Hello, everybody. Today we have the pleasure to have here Professor Torsten Braun from the University of Bern in Switzerland for the seminar called Distributed Machine Learning in the Internet of Things. And Professor Torsten is head of communication and distributed systems research group at the Institute of Computer Science, University of Bern, where he has been a full professor since 1998. He got a PhD degree from University of Karlsruhe, Germany in 1993, and from 1994 to 1995, he was a scientist at INRIA Sophie Antipolis in France. From 1995 to 1997, he worked at IBM European Networking Center in Heidelberg, Germany, as a project leader and senior consultant. He has been a vice president of the Swiss Research and Education Network Provider Foundation from 2011 to 2019. So, Torsten, thank you very much for being with us here for this seminar, and the virtual floor is yours.
Okay, yeah, thank you for inviting me for this presentation, and yeah, thanks everybody for attending today in your morning, here in the afternoon. So I'm very happy to report about some work we did, which is, I think, related to your project, which is related to the Internet of Things, but also to machine learning. So the talk is entitled Distributed Machine Learning in the Internet of Things, and it's basically based on some work which has been mainly done by Eric Samikwa, who was a PhD student in my group until recently, and then he successfully defended his thesis, and yeah, fortunately we could keep him in Bern, so now he's working as a postdoc researcher in my group and continuing his work on distributed machine learning. So first, some motivation. Probably I don't have to talk too much about it, since you are all experts in machine learning and IoT, but I think there are quite many application areas which are based on IoT technology, where we use sensors and maybe also some actors, and where the sensors and the whole systems become more and more intelligent. For example, it could be in a health application area, where maybe on IoT devices we have some machine learning models running, even some training, or in local energy systems, where, for example, we might try to predict based on measurements the energy consumption, which is quite important in order to better control a smart energy system. Also building control, you also could imagine to have some machine learning based control, where maybe based on certain parameters, heatings or cooling systems or other systems might be switched on or switched off, for example. The problem with machine learning, in particular, if we think about running machine learning models, but also maybe training on IoT devices, is that on IoT devices we have very limited processing power compared to server systems, and also storage. That means if we have a large amount of data which is sensed, maybe we cannot completely store it for some time. And one approach, what we could do is we could try to run simplified models by having a model compression on the IoT device, but typically this comes at the expense of lower accuracy, prediction accuracy, for example, if we have simplified models. Another approach what we could do is we could use cloud or edge technology. So in that case, maybe the IoT devices here are only sensing the data and then send all the data maybe to some storage or to some edge device, where then the training and the inference, the machine learning inference is performed. The problem here is, in particular, if we have a large amount of data which is sent, then a large amount of data has to be transmitted over the typically wireless network. And that could create some significant traffic, but maybe more important, we might have also many transmissions, and this could be a problem if the IoT device is maybe battery powered, and then maybe the IoT device has some energy issue. Another problem in such a solution is if we transmit all the data and store it somewhere, then we give up basically the ownership of the data, and we might have some privacy issues if all the raw data is transmitted to some server system, and that could be in particular a problem if we think about health applications, where maybe we are a little bit concerned about just transmitting raw data to some other server. So in that case, we might rather try to keep the data on the IoT device. So such an edge-based solution therefore might also not be optimal. And the approach we have been following is to try to make use of the resources of the IoT device itself. And basically what we try to do, we try to apply the so-called split learning approach, where we basically separate the machine learning model between the IoT device and the server. So in that case, we only transmit some intermediate data that has been exchanged, for example, between layers of a model. And also using federated learning, in particular, to try to increase the amount of data from different IoT devices, and try to become or develop models with better accuracy by joining the various data that has been sensed by the different IoT devices. So basically, the presentation is about how to implement federated and split learning in an IoT scenario. And basically, Eric, who was the main person working on that topic, he published a couple of papers describing these concepts. So the first two papers, they are about inference. It means in that case, we run the model partly on the IoT device and on the server, but the training is completely performed on a server. And of course, this is then not optimal, since in that case also we have to transfer all the data to the server. And therefore, the second set of papers, the other two papers, they consider to also run at least part of the training on the IoT device, and only a part of the training is then performed on the server. So basically, what I want to do is I want to go through these four papers. So this was basically the sequence of the work we did so far, from the beginning, from the rather simple approach where we only made a distribution of the inference, to the more advanced approach where we also distribute the training among the IoT devices and the servers. So the first paper was called Adaptive Early Exit of Computation for Energy Efficient and Low Latency Machine Learning over IoT Networks. That was already more than 2 years ago when we published that paper at the CCNC conference. So basically, the idea here is that we take a machine learning model and split it maybe into different parts, and maybe run one part in the cloud server, maybe another part in the edge server, and another part on the IoT device. And yeah, we want basically to split the machine learning model in a way so that certain parameters are optimized. So in particular, we had a look here on energy optimization and latency optimization. That means if we run the whole model on the IoT device, a very complex model, then maybe the computation time might be very long. Therefore, we could split the model and run part of the model on the edge or in the cloud, and then can make use of better computation power in the edge or in the cloud. On the other side, this comes at the expense that we transmit here some data, and the data transmission also might take some time. So we have to consider all the parameters. Also, if you run the whole model on the IoT device, that for sure might increase the energy consumption on the IoT device. And if we consider that too, then we might have to split the model and distribute it between the edge cloud and the IoT device. So in this figure here, we have 3 layers: cloud, edge, IoT device. In our experiments, we only considered 2 layers. That means the server side and the IoT device side. And basically, this now shows how the system looks like. So we have so in the inference, we have some input data and some output data, and the data is processed by a sequence of layers of the machine learning model. And basically what we try to do, we try to find a so-called partition point or split point. That means we want to decide where we divide the model into 2 parts. So this part then is run on the IoT device, and the other part is then run on the edge server. So in this case, only 2 systems, IoT device and edge server, and we only calculate here this partition point where we basically divide the model into 2 halves. And the complexity comes now by the fact that we want to try to always calculate the optimal partition point in a dynamic way. So basically what we assume, what can happen, for example, is that the network itself, the wireless network itself, also might change its characteristics. For example, the capacity of the network might change based on different channel conditions, or also based on different load conditions. And so in that case, maybe at one point of a time, the split point might be good here, but maybe later the capacity of the network might increase or decrease, and then we might have a situation where the split point might be better here or here. So the split point basically can also be somehow dynamic. So basically it depends very much on the network capacity, but overall we also have to consider the time it takes to process the various layers on the IoT device or on the server. So it means what we have to know also is how long it takes to to process a layer on the IoT device and how long it takes to process a layer on the server side. And here basically you see some formulas where we first calculate the energy which is consumed on the IoT device only. That means we have here for the energy consumption two components. This component basically calculates the energy that is caused by the transmission. So you see here it depends on the available bandwidth and on the amount of data and the power we need for the transmission. And this term basically calculates the time we need to process a certain number of layers on the IoT device, and this is here the power consumption for the computation. And the other formula here basically calculates the overall delay. That means if we split now the model into two halves, we have a certain delay which is caused by the calculation on the IoT device, and another part for the calculation of the remaining layers on the edge server. And we have here some time to exchange the data here at the partition point. And what we want to do is now we want to find a kind of optimum, since these parameters, energy and delay, can also be conflicting with each other. So there might also be some applications which can afford longer delay. In other cases, we have to focus more on the energy. So basically, we want to consider both the delay and the energy, and so we have a parameter alpha, which is a kind of weight whether we consider the delay or the energy this higher priority, for example. And basically, then we are looking for the split point for basically for the layer, which results then in the optimal overall value here, considering both the delay and the energy. So in this case, at one point of time, this layer here might be the optimal split point, and maybe then the bandwidth of the network changes, and that could result then in another split point. So basically, yeah, all the experiments I showed today are based on real world experiments in the lab. So there's not a single simulation. Here you see the experimentation platform. So we first used the Raspberry Pi devices as IoT devices, and the desktop computer as an edge server. We have convolutional neural network models using TensorFlow. These two models we experimented with, and here what you see here is now the delay. That means including the processing and the communication, depending on the split point. So we have now here 22 layers. That means in that case we use the AlexNet. So we have 22 different options where we select the split point, and we see here if you only consider the delay, the layer 4 would be now the optimal split point. And so in that case, we achieve the lowest delay. If you also consider the energy here, now we have a situation where also considering the energy, the optimal split point might be here on the layer 4.2. But there might be some cases where when we consider the energy and the delay, we might have different split points. But in this case, the optimal split point now was here, the layer 4. So basically, there were some other works. We compared our work with, for example, here the delay and the energy And we see that our work was performing quite well here compared to these related works, Sission and Boomerang. Okay, so this was the first rather simple work we performed. That means just selecting a split point and deciding which part to process on the IoT device and which part to process on the server side. The next piece of work we called DISNet, Distributed Microsplit Deep Learning and Heterogeneous Dynamic IoT. And basically, here I just repeat what we did. So basically, we also can call this concept I introduced before horizontal DNN partitioning. That means we just partition here in a horizontal way, and then run one part on the IoT device, maybe another part on a second edge device, and maybe this part on the cloud server. And now what we did in this DISNet, we also combined now the horizontal partitioning with vertical partitioning. That means we tried to also partition now in a vertical dimension. And yeah, you see that here. So this is horizontal partitioning again, and now you see here the vertical partitioning. And the idea was then by having vertical partitioning, for example, we also can then place here a certain set of layers and the partitioned layers on various devices in a distributed way. So basically, now we take this picture and just rotate it, and then it looks like this. So in that case, part of the data then goes into this pipeline, a part of the data here, and a part of the data here. But in reality, it's not as easy as it is shown here. But what we have to do is we also have to deliver part of the data to one other device from here and also from here. So basically, we have to copy the data also between the devices in order to support this vertical splitting we try to implement here. So the overall idea then is we might have a couple of devices, and we basically distribute then the machine learning model among all these devices. That means we try to make use of the various resources that are available maybe in an IoT network. And basically what we have to do then is we have now here one device, and we can then maybe process a couple of layers split horizontally and vertically, and place these parts of the layers on one device. Another device is processing this part, another device is processing this part, and so on. And to do that, Eric basically designed and implemented some optimization algorithm to come up with a good allocation of the resources in order to process these horizontally and vertically split machine learning models in an energy efficient way, but also in a way that we can achieve certain time limits. So again, the main parameters to optimize are time for the inference task and energy for the inference task. So you see here the formula for the delay and for the energy. And again, we want to find a kind of optimum considering the parameter alpha. That means whether we put a higher priority on the delay or whether we have a higher priority on the energy, which could be based on certain requirements by the application. So everything has been implemented and tested again in a lab environment. In this case, we use Raspberry Pi and NVIDIA Jetson Nano platforms, and we experimented with random topologies and connectivity patterns. And then also we compared again this net approach with some other related work, and we saw that our approach performed quite well. It means we could by this quite sophisticated allocation of the inference tasks then reduce the overall inference delay, but also we could basically somehow limit the energy to be used by the various IoT devices. I mentioned at the beginning that if we only have the inference distributed or implemented on the IoT device, we still have to transmit the raw data for learning to a central server. That means this is of course not the optimal case we want to have in the end, in particular if you think about privacy issues where we really don't want to send the raw data to the server system. So therefore the other two works, the other two papers we published are now concerned with distributing the machine learning itself, but again having an idea in mind to somehow optimize the training time, but also optimize the energy. So we should not overload the IoT device too much so that the IoT device runs out of energy too quickly. Also, we should consider that the IoT device only has a limited set of resources, so that the training task can be performed still within a reasonable time. So this system we developed here is called ARIS, or Adaptive Resource Aware Split Learning for the IoT. And as we will see later, we did some performance comparisons with federated learning approaches, and because of that I introduce here federated learning. So ARIS is not implementing federated learning, but we just compare the performance later with federated learning. So I guess most of you know federated learning, where we have a couple of clients where we have the models running on the clients, and then we send some model parameters from the clients to the servers, or to an aggregation server, federated learning server, where a global model then is calculated, and these global model parameters are then sent back to the client. So in that case, also we can basically make use of the data that have been collected at the various client sites, and then come up maybe with a better global model to be used by the various clients. Problems in federated learning are that we might have stragglers. That means some clients, in particular if you have heterogeneous clients, some clients might have better hardware and run the training faster than the others. So in that case, the federated learning server then has to wait for the slowest system. There might be also different network conditions. Maybe this network connection might be a good one, and the other one might be a bad one. So in that case, we have different throughput values here between the clients and the servers. So in that case, also maybe in one case, the exchange of the parameters takes longer than in the other case, and also the energy available at the various clients can be quite different. Maybe the clients might be even solar powered, and then it might happen that this client might be located in a sunny location. The other client might rather have some problems with the energy. For example, might have a smaller battery. For example, though we might have a very heterogeneous situations in terms of the computation power, in terms of the available energy, but also in terms of the network conditions. Then split learning is basically the concept we have investigated so far, but the traditional split learning approach basically worked like that we only had one split point. That means the model was basically split in a homogeneous way for all the clients, and did not consider the fact that we could have very different situations for each client. So standard split learning does not consider device heterogeneity, but also not heterogeneous network conditions, and that's basically where we want to have a contribution. So our approach should now consider different heterogeneous situations in terms of the device hardware, but also in terms of network conditions. So basically, our approach, which is now an adaptive split learning approach, basically considers the computing power on the devices, but also the potentially different network conditions between a device and the server. So here, this channel here and this channel, they could have, for example, different bandwidths because of different situations, or even different wireless technologies used. So in our approach, compared to the standard split learning, we try now to calculate for each device here again a different split point. So you see here, in this case, we have 3 layers that can be processed on this device, while in the other case, only 2 layers are processed on the device 1. And here we now support the training. In the previous work, we only supported inference. But again, now what we have to know is the time it takes for processing the various layers. That means the training time. And also we need to know the capacity of the network of the wireless channel between the devices and the server. And then we try again to find now the optimal split point for each of the devices. And again, we try now to find an optimal set of split points, considering the energy consumption, the time for the training. And so basically the result then is a so-called optimal split matrix. That means a sequence of values where we have to perform the splitting for the training for each of the devices we consider in our scenario. So basically, yeah, this is a graphical representation of the system, where you see again that on this device we have less layers than on this device, and more layers are now processed on the edge server than, for example, in this case. And again, you see here we have an optimization module. I don't discuss the algorithms. If you are interested, you might have a look on the papers to understand the optimization algorithms. And these optimization algorithm basically needs the current values for the bandwidth, which are obtained from a network module. That means we need to have some kind of observation how much bandwidth is available between the devices here and the server, and we need an estimation module which estimates the time it takes for the processing of the training on the various layers here on each device. So this training time per layer here can also be different now for each device, since we assume that the devices here also might be heterogeneous. Maybe we might have an NVIDIA device or maybe a more simpler device. So in that case, all of the processing time might be different depending on the device hardware. So you see here again the Raspberry Pis and NVIDIA Jetson Nanos we use. The Jetson Nano nodes can also be configured in different modes with higher, medium, and low performance. So we can here implement quite some heterogeneous environment. And also for the edge server, we used a regular PC then, which supported then the training. Okay, here again some results. And now basically we compare here our approach, which was called RS, with standard split learning and the federated learning approach. Here, dependent on the power modes, we could use for Jetson Nano. So here we have the overall training time and the power use, and in particular, we see here that our approach performed quite well considering the training time, but also the energy. Here we see that standard split learning and our approach is quite similar in terms of power, but we see here some scenarios then where the training time was much better using our approach compared to a standard split learning approach. Here again, further results depend on this alpha parameter, which gives a higher priority for energy consumption or for training times. Again, we see that our approach performs quite well compared to standard split learning and federated learning. Here in final evaluation results about the accuracy and the convergence time. So here you see the number of rounds, training rounds, and we compare here the accuracy of RS and federated learning, and we see that the convergence of RS was pretty good, more or less similar, or sometimes even better here compared to federated learning. Okay, and finally, I want to briefly discuss the latest work we published, which was called Dynamic Federated Split Learning Heterogeneous IoT, which recently was published in an IEEE Transaction journal on machine learning in networks. And basically what we do now here is that we integrate now both the federated learning and the split learning approach together. Before we only had split learning and an adaptive version of split learning. So basically we combine now federated learning, which is depicted here, and the split learning approach. So this work had also some other work we compared with. So other people did this combination already before. This work was called federated split learning. But again, that work had always the same split point for all the devices. So in this work, heterogeneity and adaptivity, for example, based on the current network conditions, was not addressed. And we basically extended that work considering the heterogeneous devices we might have in a scenario, but also the adaptivity mainly because of varying network conditions. So basically, this is now the operation of our approach. So basically, you see here again that depending on maybe the network conditions, but also depending of the hardware we have available, the split points could be different. So in that case, 2 layers were processed on the device E, 3 layers on the device B. So in that case, then we had to run more layers on the server or less layers depending on the device heterogeneity and the channel characteristics. Also, we used here a federated learning approach. That means all the model parameters from all devices were aggregated by parameter server. And the main objective was here to minimize the loss function here. So these are the typical formulas you might know from federated learning. So we also integrated some additional methods. Basically, you already saw these estimation modules and the network modules before. So the estimation module had to estimate the time needed by each layer on each device, depending on the hardware characteristics. Network module had to periodically estimate the throughput of the wireless channel. In particular, to support federated learning, we also implemented so-called model clustering. That means we created groups of devices that had similar data distributions. And so basically we grouped these devices together and then aggregated the model parameters of these groups of devices that can also be used for outlier detection. For example, also to detect possible attacks. For example, if a device tries to somehow transmit some fake data in order to make the model worse, that also could be detected then by such a grouping approach and by implementing so-called outlier detection. Again, we had to do some optimization, similar parameters as before. Basically now we wanted to minimize again delay and energy as before, but also now we have to minimize training loss. So you have the formulas here for calculating the delay, the energy, and the loss. And now we have three weight parameters, beta 1, beta 2, beta 3, depending on whether we focus on optimization of the delay, the energy, or the training loss. And basically then we have to come up again with optimal split points so that we achieve our optimization goal in a very good way. Again, experiments using Dresden Nano and Raspberry Pi system. You see here the data set we use for having some baseline to compare the various approaches. And now we compare here our approach DFL with standard split learning and standard federated learning. Here the training time, the energy, and the accuracy, and I think this is also the time, or some time here. And you see here that in most of the cases our approach performed quite well compared to the other approaches, and in particular compared to the standard SFL, we have the advantage that we really can react on fluctuations in the wireless channel, but also can better support heterogeneous devices. Okay, this brings me to the conclusion. So I promise to finish after some 45 minutes to have some time also for discussions. So I tried also to motivate that machine learning is in particular in IoT scenarios moving towards distributed approaches because of different reasons, optimizing the computation resources, but also because of privacy concerns, in particular when we don't want to distribute raw data. We saw that processing at end devices has some advantages, but also some disadvantages. So we have to be very careful to decide what kind of processing load we put on the IoT devices. We always have to consider that maybe an IoT device has limited energy in case of battery or solar power driven devices. So in that case, it might be a good idea to integrate end system and edge or cloud processing. That means make use of the processing resources we have in an edge or cloud server environment. And I didn't talk too much about the algorithms. They are a little bit complex. Maybe you can also have a look on the papers then. But this was not quite trivial to come up with an optimization approach, in particular when we have conflicting parameters. So in one way we want to optimize the energy, but in the other way we also maybe want to optimize transmission amount or the transmission of parameters. And this somehow requires to have some balance of distributing the machine learning model across the IoT devices and the servers. So what's next? A little bit an outlook. I mentioned that federated learning might be good for privacy, but definitely this is not enough. So there might be additional mechanisms like, for example, more protection of the data, adding some noise. Differential privacy, for example, is often discussed in such a scenario. Our current research also goes a little bit away from federated learning, where we have a central federated learning server, but we try to come up with mechanisms where we have a fully distributed or decentralized machine learning approach, where basically the end systems themselves become more or less federated learning servers. In particular, that can be also quite attractive in vehicular networks, where maybe we don't have to look too much into energy limitations or processing limitations. Since in a car we have maybe sufficient energy, but also maybe in future cars we have maybe a couple of GPUs even maybe. We are also looking into how to come up with distributed machine learning approaches, in particular federated learning approaches in 6G network. We have a project on massive MIMO, in particular beam steering, when we want to have directional transmissions in a massive MIMO environment, also using federated learning in that case. And then we have some use cases where we work with other researchers, for example, have a look on how to use federated learning in a smart metering environment, and also a use case in psychology where the psychology researchers, they are interested in analyzing smartphone data and come up with some models which allow them to predict or to identify whether a person maybe is stressed, or whether the stress level has even become worse, and in order to find out whether maybe there is a critical state of a patient, for example, and that also can be used or can be based on machine learning implemented on smartphones. And in that case, we have, of course, also a very severe privacy issue we have to consider, and therefore we think that federated learning can be quite useful in such an application scenario. Okay, that's basically it. I thank you so far for the attention, and I would be happy to discuss whatever question you have. Thank you.
Thank you, Torsten. Thank you very much for your excellent presentation. Now we'll open up for questions, since there is this 10-second delay to YouTube. Most people are in YouTube. So I will ask my first question. So I've been working with IoT for agriculture, and there are some sensors that run on batteries. And then you mentioned about like different splits strategies, some of them like more layers, less layers. And so do you think that sensors that run on batteries can really participate on that split computing, because they have to save battery for lifetime, so.
Yeah, I mean, that's a good question. I mean, if you have IoT devices which only have a battery and maybe not an additional source like a solar panel, for example, then you really have to be careful. I mean, you saw we rather experimented with devices like Raspberry Pis and so on, but I think at least for such devices, it might be feasible that, for example, if you have a solar panel or some other kind of energy harvesting, that you might harvest enough energy, though that basically some additional machine learning processing tasks can run there. But I agree, if you only have a battery which have to last for a year or two, of course, then it might be critical.
Yeah, thank you. This is really a concern. So we are still waiting for questions. I wonder, like, if someone I could ask. Okay, here. Then the question is, when using IoT device processing for the distributed model training, is this the full computational capacity considered? How is the optimal threshold set to avoid impacting primary functions like sensing, actuation, and can this threshold adjust dynamically based on device status? So it's a kind of a complex.
I'm just reading it again. Yeah. Sorry, I just need a couple of seconds. Okay. Yeah. Yeah. Okay. I mean, of course, if I understand it right, of course, if possible, we try to use the full computation power of the device. But if we use the full computation power, then we might have an issue with the energy. Yeah? If the device is permanently computing, then of course we need more energy than if the device is only part of the time computing, and we could switch on maybe a power saving mode. So this basically is somehow reflected on the energy we are considering.
Okay, thank you. Let me see there. Okay, I'm just wondering. So I think okay. I'm just asking another one. So about like the optimal partition of the split point. Um, do you consider like several layers, or because in the picture you had like one like device layer and then the edge support layer, and then you mentioned that this is optimal partition. I think it was in the first paper that you have like that picture and you varied the partition point, something like that, you know.
Yep.
Yeah, then you consider like I would say stages, like the device
Yep.
and the edge or the cloud, or
We,
more, or
we consider two device layers, an edge server and the IoT device here only.
okay, the edge layer you are considering to be like also a device layer, and not like some
So
support with more processing power.
yeah, here we assume to have a kind of PC-like system.
Okay, so then
So for the abbreviations, we use the here desktop computer with enough resources, not no GPU, but yeah, some higher performance CPU. At least compared to the Raspberry Pi, significantly more powerful.
okay, thank you very much. So we have another question here in the chat about the heterogeneity of processing power and connectivity across IoT device.
Okay, just reading it. I mean, in the federated learning approach, basically, okay, we first of all we have the same network architecture across a node. Sorry, the same network architecture across the nodes. So we the only thing then is we have to adapt the parameters then. And in the federated learning approach, this is then done by the aggregation server, which basically aggregates the parameters and redistributes the parameters to the nodes. Otherwise, in the third work where we don't have the federated learning, then we might have individual networks for each of the devices.
Okay, thank you. We still have time for more, like one or two questions. If you could send, I just to wait because of this delay from our room here to YouTube. So if you could send questions. I'm just waiting for more questions. I don't want to make all my own questions. So let's see if there are more questions. let's see. Okay, I'm just seeing here. So then I think it's okay. If we don't have any. Okay, now we see here another question. So the question is like in YouTube is like, when using IoT devices for processing for distributed model training.
I think we had that.
Oh, no, okay,
already.
okay, that's one we had. Okay,
Yeah.
so okay, yeah. I'm just saying here. So people are just saying thank you very much. A lot of
I can see it.
people. Yeah. So yeah, that's it. So
Okay.
I think we don't have more questions. So I'd like to
Thanks
thank you
everybody
once
for
more.
attending. Appreciate your time.
Thank you for taking your time to deliver this talk to us and participating in this seminar series of our National Institute of Science and Technology. So thank you very
everybody.
much. Thank you all of you who follow us and connected. Sometimes they are connected right now, and I'd like to thank all of you who will watch this video afterwards in our channel at YouTube. So thank you very much. We are closing the streaming right now. So bye, Torsten. Thank you.
Thank you. Bye.